In this lesson, we are going to look in more detail about assigning positive and negative for clockwise and counterclockwise rotation. And the most important thing is that we immediately jump to this image here and that we think of the direction of the omega vector, which we have here. So our omega vector direction is going to be based on the convention that we use this right-hand rule or right-hand curl, where we aren't really going to think about clockwise and counterclockwise, because we're going to see in a moment that counterclockwise and clockwise really depends on perspective, and it fails us when we need to do actual addition and subtraction mathematics on the rotation. So let's not talk about clockwise and counterclockwise for a moment, and let's just say we have a disk spinning with this type of motion. So that's the motion, that's the spinning motion we see. Well, the convention is the same as our cross product. We're either going to be in a karate chop position or what I call the reverse karate chop position, which is that more awkward twisting of your hand. But hopefully the image here is drawn very well, so you can see that they're in a karate chop position. Their pinky is to the disc. They're going to be able to curl and make a fist naturally and stick the thumb up, and that would be a positive up omega vector rotation. So the actual rotation is down here, but that's the omega direction that we assign. Now, if the disk were spinning in the other sense, and we can only have two ways a disk can spin, either in the clockwise or counterclockwise sense, but let's just say it's in this pink sense. Now, practice it with me. Reverse karate chop. So to make a fist naturally, we have to spin our hand over, get it in that awkward reverse karate chop position, make the fist thumb down. So now our omega vector is down or negative, and that's going to allow us to add and subtract when a disk maybe starts off spinning the way the green is given here in this sense, but maybe it's slowing down. So the force that's going to be slowing it down is going to be actually pushing in this other sense to have it slow down, just like when we did acceleration and deceleration, speeding up and slowing down in a linear sense. If the velocity and acceleration were in the same direction, either both forward or both backwards, that object was speeding up. If the acceleration is in the direction opposed to the velocity vector, then the object is slowing down, whether the velocity is positive and acceleration is negative, or the velocity is negative and the acceleration is positive. Now, the perspective issue is shown here, and I know it can be a little difficult to see, especially on a two-dimensional sheet of paper, but let's handle what I think is the easier one to look at, and that's the pink one. So we will be working almost exclusively with rotations in the plane of the page, and we will be where we naturally are, outside, looking in at the plane of our page. So if I see a rotation that is clockwise, right? Goes the way the clock goes. So I would say that's a clockwise rotation. I'm out here. Now I have that awkward reverse karate chop. So I'm in the plane of the page, and I have to spin my thumb. My thumb is into the paper. So as far as you getting your homework problems correct, as long as you will focus, solve it within the plane of the page. If it's clockwise, it's going to be that reverse karate chop, thumb into the paper. Obviously, if it is counterclockwise, now it's the more natural. I'll spin my fingers, karate chop position, spin my fingers in the green position, thumb out of the paper. So if you understand that, you're in good shape. Now, the perspective from behind that I have shown here is that the blue person, it may take your eyes a little bit to adjust to this, but if the blue person sees the same rotation as the pink person, so the wheel is spinning in this sense, I hope you can see that this person is actually going to see a counterclockwise wheel. So they would say, I'm viewing a wheel that's spinning counterclockwise. Now, however, if they do the right hand, so if they use their right hand and do the curl properly from their perspective, they will still have a negative z hat thumb pointing at them. So very difficult to show on a piece of paper. We can talk more about it in class, but we are now consistent. One person does not disagree with the other, that we have clockwise versus counterclockwise. They both say, I agree, we have negative z hat rotation, we have negative z hat omega. Yes, I agree, we have negative z hat omega. And what I have down here is just illustrating, again, the notion that we have to be able to add and subtract clockwise from counterclockwise, now I'm referring to in the plane of the page, because as you can see here, if we have a negative z hat omega vector, so we're associating our clockwise rotation in the plane of the page, and please get used to working within the plane of the page. That's my reverse karate chop, thumb into the paper, negative z hat. If the acceleration is also negative z hat, then what that means is this wheel is speeding up as it's spinning, so it's getting faster, 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 and that is exactly the same as what we saw in linear velocity and acceleration for speeding up and slowing down, so it works the same. You will get more comfortable with this as we go along, I promise you, and we're going to be doing it for both Chapter 11 and Chapter 12. All right, so let's quickly go back and just refresh, go on to the next page now, and refresh our memories on period of revolution, frequency of revolution, and we're going to now introduce our omega into that mix as well. Well, whether we have a point particle moving in a circle or a complete wheel moving in a circle, the period of motion is the amount of time it takes to complete one revolution. So period is time, one revolution. Frequency is the number of revolutions per second, and revolution is a word, not a unit, so they could use revolutions or cycles per second, you'll see sometimes as well. So the actual unit is over here, 1 on seconds. So that's the unit for frequency. And just as we had for circular motion, the frequency and period of motion are reciprocals of each other, so it's intuitive, I think, that if you have a frequency of 1 revolution per second, that means that it took 1 second to go around. But now if you're speeding up, right, you went to 2 revolutions per second, well, it only took a half a second to go around. So they are reciprocals of each other. Now, when we convert from revolutions to radians, so let's say we were given a certain number of revolutions per second, and we just converted to radians per second. Well, radians per second, that sounds familiar. A radian per second is an omega, and it is. So we can put omega there. And what did we have to do? We multiplied by 2 pi. So omega equals 2 pi f, that is going to become part of our arsenal of equations that we use, so please highlight that or mark that up. And what is really important for you to know as far as problem solving goes, which everybody wants to get the problems correct when we go to solve them, is depending on the language that's used in the problem. They may use angular velocity and refer to it as omega. They may also use this language angular frequency because omega also equals 2 pi f, but to you, there's no difference. These are the same things. They're just different words. Radians per second, omega equals 2 pi f, whether it is introduced to you as an angular velocity or whether it is introduced as angular frequency. So, conventions, refreshing our knowledge already of period and frequency. The conventions for the omega are important. We will be doing a lot of that, and as I said, I promise you will get better at it. And we will be moving on.